Hello everyone, welcome back to Math 143, Finite Mathematics. In our previous lecture, we learned that a system of linear equations can have one solution, infinitely many solutions, or no solution. Today, we will focus on systems that have one unique solution and learn several methods for solving them. By the end of this lecture, you should be able to solve systems using the elimination method, understand elementary row operations, and write an augmented matrix, solve systems using the Gauss-Jordan method, recognize matrices in reduced row echelon form. So last time we learned that the solution of system is the point where two lines intersect. Today, instead of graphing the equations, we will use algebraic and matrix methods that are much more efficient, especially for systems with 3 or more variables. The elimination method. So, the elimination method solves systems by eliminating one variable at a time. The goal is to simplify the system until only one variable remains. The transformed system always has the same solution as the original system. Right? So the allowed row operations are for the elimination method. So swap or interchange any two equations. Swap or interchange any two equations and multiply an equation by a non-zero constant. Also, add a multiple of one equation to another. These are the operations and we call them as elementary operations. Right? Swap two equations. Multiply an equation by a non-zero constant and add a multiple of one equation to another. So these operations are called elementary operations. Okay, let's see the example. Here you can see the system with two equations, 2x plus y equals 7, 2x minus y equals 1. So as of the step 1, add the equations to eliminate y, since you can see that the plus y and negative y here, by adding these two equations, we can easily eliminate the y, right? Let's see the steps. 2x plus y equals 7, 2x minus y equals 1. By adding these 2x, 2x, 4x, plus y negative y, 0 equals 8. Finally, we have 4x equals 8. Then solve it for x equals 2. Then as of the step 2, substitute x into the one of the equation. Let's use substitute x equals 2. Then 2 times 2 plus y equals 7. 4 plus y equals 7. Y equals 3. Therefore, the answer should be xy, x equals 2, y equals 3 is the unique solution. This is how the elimination method works. Okay, let's go for the 3 variable system. Solve the following system of equations. You can see that introducing the system 2x plus 4y plus 6z equals 22, 3x plus 8y plus 5z equals 27, negative x plus y plus 2z equals 2. Okay, instead of solving everything at once, we eliminate one variable at a time until we obtain a simpler system. Right? So first, think about, we have 2x, 4y, 6z, 3x, 8y, 5z, negative x, y and 2z. So let's number the equations. 1, 2, 3. So it is easy to remove the x from 1 and 3. Then let's 1 plus 2 times, okay, before that 2 times 3, multiply the equation 3 by 2, negative 2x plus 2y plus 4z equals 4. So each coefficient must multiply by 2. Now we have the fourth one, and then 1 plus 4, 2x plus 4y plus 6c equals 22, negative 2x plus 2y plus 4z equals 4. Adding all together, 0x, 6y plus 10z equals 26. Okay, 6y plus 10z equals 26. Fifth one. Then next, what should we do at next? Then next, multiply the equation number 3 by 3. Then you can see that 3x plus 3y plus 6c equals 6. Multiply each coefficient by 3. Then we have equation number 6. Then equation number 2 plus equation number 6. 3x plus 3y plus 6c equals 6. Negative 3x here. Okay, 2 plus 6. 3x plus 8y plus 5z equals 27. Negative 3x plus 3y plus 6z equals 6. By adding this together, 0x, 11y plus 11z equals how much? 33. So we can simplify this. Y plus z equals 3. Equation number 7. Okay, now then we can get the equation number 5 and number 7. Now we can see that both number 5 and number 6 only have y and z. Then let's use the elimination method. So number 7 multiplied by 6, number 7 multiplied by 6 or 10, either way, number 7 multiplied by 10, 10y plus 10z equals 30. This should be number 8. Then number 8 minus number 5. What happened? 10y plus 10z equals 30. 6y plus 10z equals 26. Minus negative subtraction. 10 minus 6, 4y. 10 minus 10, 0z. 30 minus 24, 26, 4. 4y equals 4, y equals 1. Y equals 1. Then substitute y equals 1 into 7, y plus z equals 3, then c equals 3 minus 1, 2. Okay, now we know y equals 1, z equals 2, then using any equation from 1 to 3, let's use negative x plus y plus 2z equals 2. Then negative x plus 1 plus 2 times 2 equals 2. Negative x plus 1 plus 4 equals 2. Negative x equals 2 minus 5. Negative x equals negative 3. So this gives us x equals 3. So x equals 3, y equals 1, and z equals 2. It's a long process when the number of variables increases in the system. So this is how the elimination method works, right? So within the elimination method, the goal is to simplify the system until only one variable remains. Right? The transformed system always has the same solution as the original system. Okay, then pause the video and try this example in yourself. Okay, the next thing. Instead of writing all the variables repeatedly, we can use the augmented matrices. We organize the coefficient in matrix, which is called the augmented matrix. Right? An augmented matrix is a compact way to represent a system of linear equations, and it combines with the coefficient of the variables and the constant on the right hand side. The general form, you can see that we have the n variables, x1 up to xn. So we have the system of linear equations. The augmented variable matrix, we can write it in the easiest way. The coefficients, let's say x1, x2 up to xn here, and by adding the vertical line, the constant term. So the all coefficient for the first equation in the first row, constant term. All coefficient in the second equation for the second row, the constant. For an example, here you can see that the x plus 2y equals 5, 3x minus y equals 4. It becomes an augmented matrix. So the matrix x, y constant. For the first equation, we have coefficient of x 1, coefficient of y 2, constant term 5. Second equation, the coefficient of x 3, coefficient of y -1, and the constant. Notice that the left side contains the coefficients and the vertical line separates the constants. So this notation saves the time and simplifies the calculations. Okay, then solving systems using the augmented matrix or matrices. The matrix method follows 4 steps. The first one, write the augmented matrix. Write the augmented matrix. Second, perform elementary row operations, use elementary row operations, and reduce the matrix to row echelon form or reduced row echelon form. We will look for the row echelon form and reduced row echelon form later today. So finally, read the solution directly from the final matrix. Interpret the final matrix to find out the solution. This process is especially useful for larger system, right? Okay, now first we wanted to know the row reduced or reduced row echelon form. So reduced row echelon form, which is called RREF. Let's explain the characteristics of RREF. So the 0 rows appears below all non-zero rows. So 0 rows are at the bottom. And every leading entry is 1. Each leading 1 appears to the right of the one above it, and every leading 1 is the only non-zero entry in its column. I know there's a confusion. Let's see the example. Here we have, Here we have the simple example 1 0 0 1 2 3. So 0 rows are at the bottom. See the leading ones. We have x, y, the x and y, 2 leading coefficients. Every leading entry is 1. So here 1, here 1. Each leading 1 appears to the right of the one above it. So you can see that right of the one above it. 0 rows are at the bottom, and every leading 1 is the only non-zero entry in its column. That means when we make the leading coefficients are equal, all other entries below that leading coefficient and above that leading coefficient must be equal 0. So immediately we can read this matrix as x equals 2 and y equals 3. Right? Okay. Let's go for the example here. First, write down the augmented matrix. 2, 3, -1, 1, 4, 1, 2, 5, -1, 2, 3, 4. Using row operations, we wanted to convert this into the reduced row echelon form. Okay, let's convert. Okay. First, the first leading coefficient here, 2, we wanted to convert that coefficient into 1. So row 1, R1 row 1 divide by 2 goes to R1. So all others are remain unchanged. 2 divided by 2, 1, 3 divided by 2, negative 1 divided by 2, and 1/2. All others remain unchanged. 4, 1, 2, 5, negative 1, 2, 3, 4. Next. Now the leading coefficient here is 1. Then let's remove the bottom lines. Okay. R1 plus R3 goes to R3. You can see that negative 1, positive 1, negative 1 goes to 0. Then 0, R1 plus R3, 1/2, then 5/2, 3, negative 1/2, 5/2, here 7/2, and 4 plus 1/2, 9/2. Then others remain unchanged. Okay, the next target would be number 4. Then use the row operation. R1 let's get one more page here. R1 R2 minus 4 times R1 goes to R2. So then we can see that R2, 4 minus 4 times 1, 0. 1 minus 4 times 3/2, negative 5. 2 minus 4 times negative 1/2, 4. 5 minus 4 times 1/2, 3. All others remain unchanged. Okay, so now with the first leading coefficient here, all bottom rows are 0 now. Then the second leading coefficient would be this. We wanted to convert that into 1. So to convert it into 1, let's use R2 divided by negative 5 over R2 multiplied by negative 1/5 goes to R2. All others remain unchanged. 0, 1, negative 4/5, negative 3/5. 1, 3/2, negative 1/2, 1/2, 0, 7/2, 5/2, 9/2. Okay, then what should we do next? Next, I am going to I'm going to multiply before that. Yeah, multiply the R2, now we want to remove these two. These two should be 0. Then R2 multiplied by 7 over 2 minus R3 goes to R3. So 0, 0, then negative 4 over 3 times 4, 5. Negative 4 over 5 times 7 over 2 minus 5 over 2. Okay. Negative 14 over 5 minus 5 over 2, 10, negative 28, negative 25, negative 53 over 10. Next, negative 3 over 5 times 7 over 2 minus 9 over 2. Then we have 10 here, negative 21 minus 45. All others remain unchanged. Okay, then let's simplify the R3 by multiplying 10. The easiest way. 1, 3 over 2, negative 1 half, 1 half, 0, 1, negative 4 over 5, negative 3 over 5, 0, 0, negative 53, negative 66. Okay, next step. We wanted to remove this. To do that, R1 minus 3 over 2 times R2 goes to R1. Okay, so then 0, 1, negative 4 over 5, 3 over 5, 0, 0, negative 53, negative 66. And here 1, 0, R1 minus 3 over 2 times negative 4 over 5, negative 1 half plus over 10. Seven over 5. And this way 1 half minus 3 over 2 times 3 over 5. Again, oh, this one is wrong. I'm sorry. This should be negative 4. Oh, No, it's correct. Okay. Let's see. 5 plus 9. 14 over 10. Again 7 over 5. Okay. Now, next step. We wanted to convert this, we wanted to convert this into 1. To get that, R3 over negative 53 goes to R3. 107 over 5, 7 over 5, 0, 1, negative 4 over 5, negative 3 over 5, 0, 0, 1, 66 over 53. Okay, then at last we wanted to remove these two. To do that, we can handle it easily with R3 times 4 over 5 plus R2 goes to R2. So that is 0, 1, 0. Then 66 over 53 times 4 over 5, negative 3 over 5. Simplify the value. $264 minus 159. So the value should be 264 minus 159, 105, 53 times 5, 21 over 53. 21 over 53. So all others remain unchanged. 0, 0, 1, 66 over 53, 0, 0, 7 over 5, 7 over 5. Then easily remove this. Use the operation. Use the operation. R3 7 over 5, negative 7 over 5, negative 7 over 5 times R3 plus R1 goes to R1. So R2 and R3 remain unchanged. Then 1, 0, 0, negative 7 over 5 times 66 over 53 plus 7 over 5. 5 times 53, 66 times 7, negative 462 plus 53 times 7, 371. Negative 91 times negative 91 over 5 times 53, 265. Okay, finally you can see that we have 1 1 1, all others are 0. The reduced row echelon form achieved, RREF. Then from this, x equals negative 91 over 265. From this, y equals 21 over 53. Z equals 66 over 53. Read the corresponding coefficients. Okay, you can try this by yourself. And next, the Gauss-Jordan method. Introduce the 3 elementary row operations: row interchange that we discussed earlier, swap 2 rows, row scaling, multiply a row by a non-zero constant, row replacement, replace one row by itself plus a multiple of another row. These operations gradually transform the matrix into RREF. Usually this method is called the Gauss-Jordan elimination method. So this is the swap 2 rows, and this is row scaling, multiplying a row by a non-zero constant, and the row replacement, replace one row by itself plus a multiple of another row. These operations gradually transform the matrix into RREF. Okay, here is an example, the simple example here. Solve the system x plus y equals 4, 2x plus 3y equals 9. Right? First, write the augmented matrix. So we have 2 equations, 1, 1, 4, 2, 3, 9. First, write the augmented matrix. Then use the given row operation. R2 minus R1 goes to R2. R2 minus R1 goes to R2 to eliminate X. Then we can eliminate Y from row 1. Right? So to eliminate this, R2 minus 2R1 goes to R2. So R1 remain unchanged because we have the leading coefficient 1 here. Then zero, R2 minus 2R1, 3 minus negative 2, 3 minus negative 2, 3 minus 2, 1, 9 minus 8, 1. Okay, automatically we got the 1 here, the second leading coefficient. Then we wanted to remove this, right? To convert it into 0, use the operation R1 minus R2 goes to R1. So the R2 remain unchanged. R1 minus R2, then 3. Finally, the final matrix becomes the RREF form, the reduced row echelon form. You can read the solution. From the first row, x equals 3, second row, y equals 1. Right? Okay, this is how the reduced row echelon form and Gauss-Jordan method, Gauss-Jordan elimination method works. The more and more practice can get the superior experience for this one. Okay, let's see some special thing, the unit columns. A unit column is a column in a matrix where one entry is 1, every other entry equal to 1. So the unit columns make the solution easy to read in RREF. So you can see that. So within the RREF matrix, we have 1, 0, 0, 1, 3, 4. The unit column. So one entry is 1, all other entries are 0. The first column, one entry is 1, others are 0. If needed more, we have 1, 0, 1, 0, 1, 0, 0, 0, 1, 3, 2, 4. So one entry is 1. All others are 0. All others are 0. Right? So a unit column contains only one entry equal to 1, every other entry equal to 0. Okay, so the practice purpose, I would like to add the exercise here. Use 2x plus 4y equals 8, 3x minus 2y equals 4. Pause the video and solve. Try both elimination method and augmented matrix method. Okay, so today we learned several powerful techniques for solving system of linear equations. We discussed elimination method, elementary row operations, augmented matrices, reduced row echelon form, and Gauss-Jordan elimination. These methods will serve as the foundation for matrix algebra and many applications in business, economics, engineering, and computer science. So that we will study throughout this course. Okay, so try most of the examples and homework problems by yourself to get the more experience with the elimination and the augmented matrix method. Okay, thanks for watching. Let's meet with the next section.